Hey, Jessica.
Hello.
All right, we are ready to roll here, I think. All right, welcome everybody to class number 6. So today we're going to continue our journey. We're going to revisit RAG a little bit. We'll review what we did, and we're going to talk about another function called re-ranking, and then we'll start dipping our toe in the water of frameworks for AI with LangChain. So we'll try to get through both of those today. If we don't, we'll continue some of it over to next week. But I think the LangChain will be a kind of a brief introduction. What we'll do is take our code from last week. We'll add a re-ranking function to it, and then we'll sort of convert everything over to LangChain, so you can kind of see what the differences are. So we'll just review kind of what are we working on. We're building out a little app to automatically respond to trouble tickets with helpful responses using LLMs in a whole bunch of different ways. So we're trying to, I think the main goal is to demonstrate a bunch of different ways you can use LLMs within an app. So let's review a little bit about what we talked about last week with the last 2 weeks with retrieval augmented generation, RAG or RAG. So basically, it's a way to combine search with AI generation to provide better answers. So uh, we take a query, well, first, I guess in preparation, we create a vectorized database where we take documents, we run it through an embedding process, we store the text with vectors that allow us to search by meaning, also called semantic search. And then we take a query from the user, we do the same embedding to the query, we get a vector, and then we can find text chunks in our database that have a similar meaning or similar context. We grab a bunch of those, we bundle them up, we take the user query again, submit it to the LLM, and ask the LLM to answer the query given a bunch of text that we found in our database. Um, so that's sort of the general process. The advantage here is that we can force the LLM to answer in a certain way. Remember, we kind of talked about the fact that LLMs sort of have two superpowers: generating unique responses, but also, um, you know, language manipulation. So they have knowledge embedded in them, but they also have the ability to manipulate language. So when we do RAG, we're mostly leaning on the language manipulation and not so much on the knowledge. Why do we do that? Well, we can get away with smaller models. The small models still have good language manipulation skills, but they may not have as much knowledge of the world embedded in them. So if we provide the knowledge, how to troubleshoot a Cisco 2732 router, we give the LLM that knowledge and just ask it to answer a specific query given that knowledge. Even a small model will do a really good job of that. So we can get by with small models. They're cheaper to run, they're faster, they're snappier performance, and if we give them the right information, they can answer the question just very nicely. So uh, also we prevent by grounding the LLM with context, we eliminate hallucinations, which is a common problem. And this is true even with the most current models. And I don't know if you've done any sort of IT type troubleshooting with current models, but a really common pattern that I see is I'll ask it a question. Um, I'm trying to use Visual Studio to do XYZ and it's not working, or how do I do it? It'll give me an answer. I'll try that. It won't work. I'll give it the error I get. Then the very next thing that it gives me is, oh yeah, the interface changed in 2004. So, well, why did you give me the previous answer then? So you can see the LLMs. I guess I wouldn't necessarily call it hallucinating, but they often give shallow answers or poorly thought through, unresearched answers. And we can avoid that. We certainly don't want that if we're building an automated trouble ticket answering system. We don't want it to give a poor answer using an old information. So um, by gathering the information that we want and providing it to the LLM, we're short-circuiting a lot of problems. So again, we're just in the review mode here. We do this embedding process. We have a specially trained model that all it does is it converts text to vectors, to numeric vectors. We can then, there's a very simple process to compare two vectors to see how closely related they are. Essentially, if you remember your linear algebra from college, and I'm sure you all took many linear algebra courses and remember every bit of them, uh, they the it's easy to compute the cosine between two vectors using some simple matrix arithmetic. And so we can determine how close two vectors are by using this cosine similarity process. It's not exactly how the search process works. When you're looking at millions of chunks of text, to compare every single one of them to do a search would be a pretty slow operation. So there is a hierarchical sort of search process in vector databases that optimizes the search process, but at the very root of it, it's a cosine similarity type problem. So we can also use metadata to refine the search and so on. So there's lots of different things. And we used a database called ChromaDB, which is something that's pretty easy to install on your machine. And it's very, very, very fast up to a certain point. Probably run a few 100,000 chunks of text on your laptop and have no problems. But basically, the idea is we just translate a chunk of text and we get a vector. We can, depending on the embedding model that we use to generate the vector, generally the smallest vectors are about 384 parameters. I'd say most modern ones are well over 1,000 parameters. So you get a pretty nice semantic meaning from that. It can encode a fair amount of information. So again, we talked about how to kind of evaluate our system, and what we did was we have about 4,000 tickets in our CSV. We divided that into an 80-20 split where we encoded 80% of the vector, 80% of the tickets into vectors and stored those in the vector database. We held out 20% for testing. And that's a pretty common split. As you advance in machine learning and AI, typically you're going to do 80-20. Now, there's another way to do this. So if you think about it, one thing we don't want to do is we don't want to, if we have this 20% we're holding out, the reason we do that is we don't want those answers already in our database. Because if we do a vector search, of course, it's going to match the text perfectly. We don't want that. We want it to pretend it's a net new ticket. So in testing, we hold out 20% of our data so that we can do proper testing. Now, one thing is if we do that and we repeat and we do a lot of testing and we do some tweaking, we could start to tweak things so that they match our test set. If we start to refine parameters, especially hyperparameters and search criteria and metadata, we could accidentally sort of refine things so that they really, really match our test set. So that's not good either. So we might actually go another step where we take 70% of our data for generating the vector database. We do testing and refinement on 20%, and then we do a final evaluation on 10%. And we're not allowed to do any further tweaking. That 10% is purely a test, and that's going to tell us how good our whole process is. So that's a further refinement that you'll see in more sophisticated setups. We haven't done that here. We're not that sophisticated right now, but that's a really important thing, is to really prevent sort of back leakage of your testing process to influence the results of your testing. So we might go this extra step further in a mission critical system. But data leakage is an important concept. So if we review our end-to-end workflow, we created our pre-translated CSV. So we took all the different foreign languages that were in there. We converted everything to English. We took a test and training split. We took 80% of those. We took 80% and generated embeddings, which are the vectors. We stored that in Chroma. The vector is the key. The chunk of text, which is the subject and the body, were used as the what we're going to retrieve. Then we take a new ticket. We run that through the exact same embedding process to generate a vector. We do the vector search. We return some number of chunks of text, previously answered tickets. We submit all that context plus the original question to we used LM Studio, to the LLM, and we asked it to give us back an answer with confidence. So that was our workflow. We also added, if you recall, we kind of had two ways of doing it. We said, we only want you to look at the context we provide, and tell us if you don't have enough information. And sometimes we got back, we don't have enough information. Or we could use an augmented mode where we say, use the context provided, but also use your own knowledge and create the best answer you can from the combination. So we can go either way. It really depends on what we're trying to do. If this is a general troubleshooting system, it might make sense to use, if you have a really big LLM with lots of knowledge and it's fairly up to date. Let's say you're using a frontier model like ChatGPT or GPT-5 or Claude Sonnet 4.5 or Gemini 2.5. We could probably be reasonably confident that if we give it good context and we let it answer with a little bit more information, we're going to get a pretty high quality answer. But if we're doing something like, let's say answering a legal document, we probably want to lock this down, and we only want to use data that we provide. We don't want it to have any potential for hallucinations. We also added some judgment. We added another path, another use of LLM. We gave it the answer. We gave it the original answer. We gave it our answer. We asked it for accuracy. We asked it for completeness, and it gave us some star ratings, if you remember. So this allowed us to evaluate our own answers. And we're going to kind of strip some of that away this week just so we can simplify things. But if you go back to the week 5 notebook, you can see all of that. So just to summarize, we learned vector embeddings, we learned similarity search, we created a whole pipeline, we learned about the training test methodology, we learned about using an LLM to evaluate the results of an LLM's answer, and we did some batch processing where we answered a bunch of tickets in a row. So that was kind of what we did over the last couple weeks. So now we want to move forward, and let's talk about a little bit of a problem. So with RAG, we kind of have competing goals, let's say. We would like to include a lot of context. So we would like our vector search to be a little bit loose so that it brings back as much good information as possible. But as you know, if you have a big wide net, in addition to the fish you want, you might get some fish you don't want. So maybe you want to catch a whole bunch of tuna, but if you have a big enough net, you're going to bring back sharks and octopus and sea monsters and Loch Ness monster and all kinds of crazy stuff. And if we bundle all that up and give it to the LLM, it's going to have good information and bad information, and it's going to actually potentially weaken the response. So we have an answer to that, which is called a re-ranker. And it's another model, it's another neural network that we can use as part of our pipeline. So what is a re-ranker? It's another filter. So I think you probably don't remember exactly, but when we ran the pipeline last week, we told it to bring back the top 5 results. Now, the thing is, we don't really know if the top 5 results gives us the right number of results. Maybe we're missing 5 more good answers that we could have used to answer the question the user was asking. Or maybe only 2 of them are good and 3 are garbage and not related. So by saying give us 5, maybe we're doing well, maybe we're not. We don't know. If we say 25, we also don't know, but there's a higher potential for returning bad answers, let's say. So what we can do is we can use a re-ranker. And what that's going to do, so the vector search, it only has the notion of cosine similarity. And there could be some negative things in there, let's say the opposite of what we want, but because the words are kind of similar, the meaning is kind of similar. So it could be bringing back some things that are almost exactly the opposite of what we want, but the words are close. So what we want to do is use a different process. This is called a re-ranker. It's a little bit more of a sophisticated model. It's not going to use vector search, but it's going to use more of an LLM process to go through this more limited set. So we could have 1,000,000 answers in our database, and we could bring back 20 of them very quickly using a vector search process. And then we can use a re-ranker to do a more sophisticated analysis and order those in order of the most to least relevant answers for our particular query, and we can throw out the bad ones. So now we can really get a little bit more sophisticated. So that'll help reduce hallucinations. And as a bonus, if we're using a frontier model, we're paying by the token. So if we're bringing back 20 answers of 1,000 tokens and we're submitting that all to our LLM at Grok, we're going to pay for that. So by eliminating the less relevant ones, not only are we improving the accuracy of our answers, but we're also saving money, maybe, 1/10 of a cent. But if we're running a high volume multi-user system, that could add up over time. So if we go back to our diagram of what this whole process is, we have our pre-processing where we set up the knowledge base. Now we have a user query coming in, we embed it, we hit the database, we get the top K similar documents. Now we cross out this arrow, and instead we give those to the re-ranker, and then it will filter out the irrelevant ones from there, and now our context is much tighter. Then we submit the user query along with that new context to the LLM. We get the response generated, and now we have a nice, tight answer. So that's where we stand. That's what we're going to do right now is we're going to just kind of pop in. We're going to go back to our code. Pretty similar to last week, but we're going to add the re-ranker in there. Any questions at this point? Good. I guess I've pummeled you into submission. All right. So let's look at our code from last week. Make this a little bigger. So everything's pretty similar to what we did last week. Just run through things. We've got our imports. We have our configuration. I think I tightened up the code a little bit to, kind of clean things up a little. So we have all of our configuration parameters up here, so they're not scattered all over. We're going to use the local My Mac Studio. And so we'll load our embedding model. We're loading, I have to re-authenticate with Hugging Face, sorry. Shoot. I think, hang on one sec, I gotta pop over and re-authenticate with Hugging Face, one moment.
So Tom, like there is a cloud version of the like GPT-OS 20 billion and 120 billion parameter. So maybe you can use that one.
Could be.
Like it is not a confidential data. So for like
Yeah,
testing and teaching, you can use that.
yeah. I was fooling around this morning, and I actually unauthenticated myself. But this is mainly this is for the re-ranker model is at Hugging Face, which is why I need the token. Let's see, token equals HF token. Hang on one sec. I just have to put it back. I unauthenticated, and now I have to re-add it to my secrets, which I'm not allowing you to see. So then I don't have to re-unauthenticate it again. Hmm. Hang on one second. Oh, I have to reload my configuration. Nope, that didn't do it either. I apologize for having to debug in front of you. Huh. One moment. Huh, it's got the token. It's brand new, but it says invalid token. I shouldn't even need to log in because I've already got the thing cached. Let me just see if I can get past it. I shouldn't need it because, all right, let me go back to sharing. See if it blows up again, I'll have to dive back. Hang on one sec here. Share. Okay. All right. So then we have a bunch of our helping functions, our load and split data, our combined text, our embed tickets, preparing the metadata, our load the vector DB. So we got all that loaded. Now we can load and split the data just like we've done. We can look at our data frame. It's all there. That's good. We can pick a ticket. So we've got an issue with Jira, near and dear to our heart. We all love Jira every day. And load the vector database here. Okay, we've got the vector DB loaded. It's got the 80% of tickets in our training set. Now here we're setting up more helper functions, search for similar tickets. You'll see here we've got re-rank tickets as a new function. So basically what it's going to do is it's going to call this re-ranker, and then it's going to sort everything into the re-rank score. Very simple, nothing very complicated. It's just a simple call to the re-ranker. We've got some of our other functions that we wrote last week. It's basically just a copy over from last week, except for that extra re-ranker function. So here's our test. And it just makes sure we're connected to LM Studio. We're testing that we can access the right model and that everything's working. So this was just a set of test functions. So then we have our support ticket. We chose one. We chose 5555, I guess, up there. So we're going to get the ticket. We get the subject and the body, and bunch it together. We're calling the vector database, and we're pulling 20 tickets. Now we're running the re-ranker just to grab the best 5. And the best ticket similarity before was pretty good, and I guess we increased it a little bit. So we changed the order, but we got rid of 15 tickets. So we got rid of some junk. And here's our generated answer. So our problem was we couldn't log into Jira 8.20. Now we're using the augmented version, so that's using some of its own knowledge plus some of the answers that we gave. So it's clear your browser's cache, make sure any browser extensions are disabled, blah, blah, blah. So it gave a pretty good answer. We ran it through our evaluation function. It gave it a 3.75 stars out of 5, 4 out of 5 for accuracy, 3 out of 5 for completeness. So with a 54% confidence, not huge, but I think what we find is, we can see some of the answers we gave are in the answers in our database. Clear your browser's cache, make sure your browser extensions are disabled, clear your browser's cache, make sure your browser's up to date. There's probably unplug it, plug it back in, reboot, various things like that. So these are the 5 tickets that were deemed to be the most relevant. And if just a quick scan, they look very relevant. And so they all definitely seem relevant. Now, one thing that's interesting, you can kind of see, one thing you can see is that the original similarity based on the vector search, the re-rank score is actually higher. So the cosine similarity was maybe 0.75, which is still pretty good. It's 0.731. In fact, let's look at these. Got 759. It bumped it to 969 based on the re-ranker. So the re-ranker takes these 20 tickets that we returned, sorts them by its score, and it actually has elevated some. We've got a 0.759, a 0.731, a 0.746, a 0.968 comes in at number 4. Now, to be fair, they're all basically about equal, but it's re-ranking these so you can see the effect of the re-ranker very easily here. Okay, so by adding that single step, we accomplished a really nice thing, which is we opened up our net to capture 20 possible tickets, but then we cut it back down to 5. 5 was our original top K from the retrieval engine. So we still have 5, but the quality is much better. So that's exactly what we were after. One thing that I can't remember, I'm going to go back up to the config. And actually, I was wrong. We were in strict mode, which means our answer was only using the context and the retrieved tickets that we provided. So this nice answer that we gave, sorry for all the scrolling. Hopefully it doesn't set off a seizure in anybody. This nicely formatted answer that we gave is purely based on the tickets that we returned. And in fact, it gives the sources tickets 1 through 3. And I think the reason for that is the tickets that we returned are all pretty similar, because a lot of people seem to have problems logging in, and the responses are all pretty similar. This one only had 2 steps. This one had 5 steps. This one went back to 2. This one had, I don't know. This one basically said nothing except we're working on it. So that's why it didn't use this one in the final answer, because it really didn't have anything. And same with ticket number 4, it just said we're looking into it. So these were not helpful answers, and our LLM understood that and did not include weaselly language like that in our generated answer. So overall, I'd say, based on the fact that we were limiting ourselves purely to the tickets that we had in the database, we did a very nice job answering this, and we didn't include anything like, "Hey, we don't know what's going on. We're just gonna take a look at it." So that's where things stand with our original stuff. And now for the second half, what I'm going to do is we're going to start looking at a framework called LangChain, where we're going to rewrite things using that framework to make it a little bit more of a pipeline that we can maintain more easily. So clear all the outputs. And overall, there's a lot of stuff that's going to be similar. We still need a lot of the helper functions. We still need to load the same environments and so on. So we do that. We've got our configuration. We've got our embedding model in here, just like the previous text. We're going to take 20 initial. We're going to re-rank and take 5. Now, I don't have any. Actually, the strict versus augmented, I don't have that in the code right now. So that is not really happening. I don't know if we're going to get our token problem again. Oh, nope. Our authentication is successful this time, probably because I reloaded things. So everything's working fine. So note we've got our re-ranking model loaded. So there's just a little point here. We're using this particular one, Mixed Bread AI. It's a small, very fast model specifically for re-ranking. There are many, many models. If you go to Hugging Face and put in re-ranker, you're going to find a lot of different models, and you can experiment and choose between them. This one happens to be generally well regarded, and it's small and fast. So here again, we basically have our same functions for loading and splitting data, for loading the vector database, and so on. We have our train test split just like before. We have our data frame exactly the same. Let's pick a different ticket this time. Mix things up a little bit. Screen flickering issue on a Dell XPS 13 laptop. So we've got a little bit of a different problem to deal with. So we'll load our database again. Again, I don't think you've seen any. So far, the code is basically identical. It will be when we get down to actually the LLM stuff. So we've got our generate answer, we've got our prompt, and these things in curly braces, these are things we're going to fill in, which we did kind of manually in the previous version. So we've got our pipeline functions loaded. So now we got our little test thing to make sure we're connected to our various external things. So we've got our connectivity to LM Studio. We've got our OpenAI client calling the GPT OSS 20B model over on LM Studio, and so on. All right. So we've got our user interface. All right. This is funny. I didn't open up the right notebook. We just reran through the exact same notebook. So I apologize. I thought things looked a little too similar. And I was confused as to why. Sorry about that. Let's go back to the LangChain. So you got a free extra review.
No one noticed, Tom. You can cut that bit from the video.
Yeah, that's right. I'll go in and edit that one out and save myself a slight amount of embarrassment. All right, so LangChain has its own kind of language called LCEL, LangChain Expression Language. And basically it allows us to take those functions and string them in a pipeline. So we can have an input, a couple of steps, and an output. So our pipeline, remember, is sort of retrieve the documents, format the context, send it to the LLM, and generate an answer. So we've got some dependencies to install, and that's all the LangChain libraries. We also need Hugging Face for embeddings, ChromaDB, just like before. So I've already installed everything, but I leave this in here for you so that you can download this stuff. And here's just sort of a directory of all the different things that we're trying to do a little better job of documenting things. So you've got a notebook that you can learn from. So we just loaded all those libraries. Here's all the LangChain libraries, and you can kind of see we've got prompts and a chat prompt template. We've got an output parser. We've got the chat OpenAI interface. We've got Hugging Face embeddings, but we're loading it from a LangChain library instead of from Hugging Face this time. We've got ChromaDB, but we're loading it from the LangChain library. We've got documents, we've got a retriever, and then we've got this funny thing called Runnable Lambda, which we'll talk about a little bit later. So we've got a couple of other things. We're loading the same cross encoder that we used for the re-ranker before. And then we've got our configuration, which again, this is pretty much identical to what we had before. Actually, a little bit simpler. We don't need everything in there anymore. We've got to load our CSV. We've got our train and test. That's very similar. And now we'll get into the LangChain a little bit more. So we're going to choose our embedding model. We're using the same model, except I guess this time we're using V2, basically the same thing. We have the ability here to set our device. So on Mac, I'm running on Mac Silicon, the M series, which uses MPS, which is metal shaders. That's the type of GPU it uses. If you're on a laptop that has CUDA installed, you can use CUDA and access your NVIDIA GPU. If you have none of the above, you can change this to CPU. Okay. We load our connection to our LLM. We load the re-ranker. Sorry, I've got a little confusion in the documentation. I went from V2 to V1. So I think in the config, it says V2. So I'll update the documentation later. Well, I guess as long as I'm standing here. I change it to V2 for laughs. Okay, so we load the embeddings. We load the connection to LM Studio. We load the re-ranker. We're all set. Very similar to what we did before. We create the vector store just like we did before, just a little bit more documentation here. Here, I did do a slightly different thing. I changed this so that it rebuilds the database in memory. Okay, so now we start to build the components for the pipeline, and we're building a thing called a custom retriever using the LangChain libraries. So LangChain has a pre-built retriever so that will retrieve stuff from a vector store. And we're going to add to that the re-ranker. So we're gonna build our own thing, a simple re-rank retriever based on LangChain's base retriever. So this is we're just building a new class based on an existing class. So LangChain gives us a base retriever. It's a base class for a document retrieval system. It's got all the stuff in there to go read from ChromaDB. But what we're going to do is add another step to it where we're going to re-rank using the cross encoder. So we're going to go get all of our documents. We're going to run it through the re-ranker here. That's going to return scores. And then we're going to sort according to the scores. First, we're going to append the scores to the documents. Then we're going to sort according to the scores. Makes sense. The higher the re-rank score, the higher up the document will be. And then we're going to limit it to the top K final documents. So K final is 5, K initial is 20. Those are defaults. We can alter those. So we're going to come in with 20. We're going to leave with 5 after we sort these. Very, very simple function. So we've got a few, I've got a few helper functions that are, again, very similar to what we had before. And then we start, basically, we're going to start assembling these into an LCL pipeline. And one little thing we need to understand is a thing called a runnable lambda. So basically, we have special functions that are in LangChain, like the retriever. And one thing that makes them special is that when we connect them into a pipeline, they have synchronized inputs and outputs. So they're easy. So if you're familiar with Unix or Linux, you have the concept of a pipeline, right? You can do a directory and pipeline that into grep, and then pipeline that into sort, and you can just easily on a command line pipeline all these things together. LCEL is the same idea. But here it's a little more complicated because the output of a function, we don't know exactly what that looks like. Maybe it's JSON, maybe it's text, maybe it's a CSV, we don't know. But if it's in an LCL, if it's an LCEL pipeline, then we know that the output will always be compatible with the input of another step in the pipeline. So Runnable Lambda is a wrapper around our a generic function that will guarantee that the inputs and outputs match what's before and after in the pipeline. That's really all it does. So we have our own function called format docs to context. And when we build our LCEL chain, we're just going to wrap it in this runnable Lambda concept, which is just another function, which is going to allow us to link it in the pipeline. So that's all. It's nothing too magical. It's just super there to format things. So our reg chain will look like this. We retrieve, we run our retriever, and we have defined our retriever as being our re-ranking retriever. And that's going to go into a variable called context. Then that feeds format docs to context. That feeds the question. Then we feed all of that into the prompt. The output of the prompt template goes into the LLM. The output of the LLM goes into an output parser. And this is just a string output parser, nothing special. We could feed it into a JSON parser. We could feed it into a CSV parser. We could feed it into 100 different output parsers to get really nicely structured text if we want. So step by step, we have an input query. We use that to retrieve and format similar tickets. We format that into a context string. The question is the original question, which comes from the input query, stays as is. We combine the context and the question into a prompt, same as we did before, but now LangChain does that for us, basically. It generates an answer by calling the LLM. We extract the text from the response because the response does come back as a JSON object. It has some statistics in there and stuff like that. So we have to pull the text out. So the string output that we used, this string output parser, basically all it's going to do is extract the text out of the response, and then we can print out the final answer. So very straightforward stuff. This whole thing is basically formatted like a dictionary, but instead of commas in between them, we have pipes. We have our prompt template. You can see, we have our system message. We have our user. We give it historical tickets. That's where the context gets dropped in. We tell it to answer the user question. We drop the original query in there. We have that way back up here in our prompt definition. We have a more sophisticated prompt definition somewhere in here, where we create the ticket text and format everything. So we can make that template more or less sophisticated. Our LLM, we use the Chat OpenAI function to use to take the base URL and connect to LM Studio to the endpoint. We have the output parser, doesn't need any parameters. And then we just string everything together. And we need that Lambda, runnable Lambda, to wrap around our format, our own function, to make it compatible with LangChain functions. So basically, when it boils down to it, it looks fairly simple. And here's the actual code. So here's our entire pipeline. And we are using a very simplified prompt here, which is we give it a system message, we give it a user message, we fill in the variables with context and the original query. Here's our definition of our entire working chain. We have the retriever that feeds the format docs. We then add those docs to the context, and we plop the question back in, the original query, and out comes the output. So we're going to add, this is basically, this is the retrieval chain here. This sort of sets up, this part just sets up the prompt to the LLM really. So then we say we have a reg chain, which takes the same information, creates the prompt. This is, I think this is leftover code that's just kind of not used anymore. The reg chain is what we really are using here. Sorry, I left a little chunk of code in there. Here is the full reg chain, the retriever, the formatting of the context, the question gets dropped in to the prompt goes into the LLM generates an answer, the answer is parsed, and that's it. So we've built the chain, now we can test it. Got a little bit more documentation here. All right, so, I'm gonna wanna change this from 555 to 557, so we get a different, all right, we got 557, the Dell XPS 13. So now it's running the chain. And over on my LLM Studio, I can see it's churning away because there's a bunch of different steps. So here's our answer. Now, we're not using the strict version right now. We're letting the LLM augment. So we get a nice markdown formatted thing, verify the firmware, test it with a different monitor, check the power settings, run Dell Diagnostics. Don't call us, call Dell. Seems like a pretty good, nice way to pass the buck. Quick tips, what to try next, and best regards. Send us more diagnostics if you get anything. A nice little touch, if you need immediate assistance, call our hotline, etc. So that's the chain in action. Again, once we had all the support stuff tested, here's the invocation of the chain. We do the reg chain, invoking it with a query, and then it runs through all those steps here. And these steps are just functions. So it's a clever way to kind of make a pretty easily visualizable chain of action that are built with functions that are automatically compatible with each other. So that is what we've got. So I've just got some extra stuff here. So one thing, we can take a look at what were the tickets that were retrieved. So here are the top 5. And again, here are the re-rank scores, very similar to what you saw. The top one in this case is 0.989 down to 0.987. But you can see from here, I've got a screen flickering problem, screen flickering, display issue, the screen flickers. So these are all pretty similar, obviously. And it seems like it did a pretty nice job getting 5 relevant tickets. Now, I think if you look at the database, I think what you're going to figure out is that they probably took 500 tickets and then used an LLM to like, hey, change the wording on these and generate 5 more tickets for each one. There's a lot of tickets that are very, 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 very similar. And so I think the database isn't the greatest, but it's good enough for our purposes for experimentation. So again, just in review, this is what LCEL looks like. We've got the retriever, we've got our own the retriever is a LangChain function. The format docs is our function that we had to wrap in a Lambda. We've got the prompt, which is a LangChain function to format a prompt template and insert the variables into it. We've got the LLM call, another LangChain function, and we've got the output parser, which is another LangChain function. So that's kind of it. So if we look at our original code versus the LangChain, we're kind of switching from a procedural standpoint to a declarative way of doing things. We're able to test per component a little bit easier. We can compose, we can create these functions, and instead of pasting everything together, we can actually compose them into this nice pipeline. So I've got a couple things you can try on your own in the homework assignment. One cool thing you can try, there's a hint up here how to do it, is to add streaming output. So if you use ChatGPT, you know that when you type in a question and you hit return, it doesn't sit and think for 20 minutes and then give you a block of text. It streams the output kind of a chunk at a time. You can do that with LangChain. That's a function that's built in. So you can add, instead of our call the LLM, wait for the answer to come back and print it, you can use stream instead. So that's a fun one to add. It's a nice feature. If you're going to build your own chatbot, you might want to use streaming. You can got some experiments you can run where you change the number of initial and final, see if that changes the responses. And then finally, add back the confidence scoring. So you can go back to the other RAG system, our roll it yourself, and grab that confidence and see if you can make a runnable Lambda out of that and add it to the chain. Okay, so in the future, we'll build a few more features on top of this, and we're going to add them to the LCEL chain rather than add more standalone functions. So that's what I've got for today, guys. I'll push all these changes up to the GitHub shortly, and you'll be able to download it and play around with it. I'll hang around if anybody has any questions. Otherwise, that's it for today. We ended almost exactly on time, so I'll give myself 1 gold star.
You get 5 stars from me, Tom. I appreciate it, dude.
All right, guys. I'll hang around for a couple minutes if anybody has any questions. Otherwise, we'll see you next week. Same time, same place.
It's Tom.
Thank you.
I have a
Ciao.
random question about the
Sure.
email for the karma.
Yeah.
I trusted ChatGPT, so I have to go back and fix that file. So all those 500, I read it this morning and it was like, I performed CPR at the beach. I performed CPR on the highway.
Yeah. They were a little repetitive.
Yeah.
I kind of get it, but yeah, it was, well, I mean, I certainly, I can proceed with what I've got and then plug in anything new that you give me.
Okay.
So
Yeah, I helped a neighbor at the beach. Some of them
Yeah.
they're funny, but not
Yeah.
what we do.
I murdered 17 people at the party. Yeah, I handed out $3 to homeless people at the beach.
Yeah.
Yeah, they were kind of humorous scenarios, I guess.
Yeah. I trusted ChatGPT. It was my fault. So I'm going through, I'm only on line 45, but it's going to take me a while.
Yeah, never trust but verify.
Yeah.
You always got to check the work of the ChatGPT.
Yeah. So that's what I'll be doing the rest of the day.
Yep. So I mean, you can even feed it back some examples and just say, I was looking more for this.
Or real life.
Give it good examples. Give it examples that you think are good. Go through there and pull out the 10% that you think are good and say, I want more like this. Sort of positive reinforcement works better than saying, I don't want things like this.
Mhm.
Negation, it's gotten better, but negation has always been a bit tricky.
Okay.
So you're better off giving it 100 or 10 examples of good things, of things you want, rather than 10 examples of things you don't want.
Okay, I'll try that.
So, yeah.
All right, thank
Anything
you.
else? Anybody else? I'm going to stop the recording. All right, guys. We'll see you next week.
Madam.
Bye,
Thanks,
Bye-bye.
everyone. Happy Halloween.
Thank you, Tom.
Yes.
Yeah,
Happy
happy
Halloween.
Halloween.
Bye.
Bye.